Hello, and welcome to this video presentation on explainable AI-based interventions for pre-season decision making in fashion retail. My name is Shravan Sajja, and I'm a research scientist for the AI for Supply Chain team of IBM Research. In the next few minutes, I'll share some of the work done by me and my co-authors in the area of fashion retail. One of the biggest problems confounding a lot of fashion houses is the problem of unsold dead inventory. Despite having a lot of historical sales data, most fashion houses are able to sell only 50 to 60% of their stock well, and the rest go through severe markdowns. Since fashion is heavily trend driven and most retailers operate by seasons like spring, summer, or autumn, winter, at the end of each season, any unsold inventory is liquidated. This problem of unsold merchandise is mainly due to a mismatch between supply and demand in the supply chain network. It could be that the inventory has been overproduced, or the inventory has not been distributed properly at the right location and at the right time, or the inventory has not been priced correctly. The blame for this can be clearly mapped to inaccurate demand forecasts and inefficiencies in the supply chain planning. So, the heart of the problem is our ability to accurately forecast the sales or sell through rates of any existing products or potential new products at any given location and time. Unlike other retail industries, fashion is heavily trend driven, and in every season, a substantial amount of new products are introduced. There is no historical sales data for these new products, and hence traditional forecasting methods do not apply. Also, there is an inherent risk associated with new product forecasting and introducing new products into the market. Notwithstanding the risk associated with new products, fashion houses typically introduce 60 to 80% new products every season, primarily as a business strategy to satisfy consumer demand at its peak. It enables the fashion house to stay relevant and preserve the consumer base in a world of constantly changing fashion trends and demands. Hence, we focused primarily on new product forecasting for this presentation. Now, as an example, let us consider a fashion retailer who is introducing new botanical print full sleeve top and wants to forecast the demand for this product for the next season. For this purpose, the retailer typically extracts products which are similar to this new product from the past season catalogs and averages their sales to get forecast for this new product. This forecast might get further adjusted based on relative market growth. Now, despite all the developments in the area of AI-enabled forecasting methodologies, most stakeholders in fashion supply chain still resort to such baseline approaches, primarily because of the interpretability. Hence, it is desirable that AI-enabled forecasting methodologies are interpretable and also explainable. Explainable sales forecasting models will not only improve the trustworthiness of a model's output, but also provide transparency for all stakeholders involved in different decision-making processes of the supply chain. Interpretability of a model is the degree to which a human can understand the cause of a decision made by the model. Explainability for a prediction model can be achieved by equipping the model to answer questions like how do different inputs of a model can affect its predictions, or what is the relative credit or blame that can be ascribed to different inputs for a particular prediction. Explainability improves accountability and fosters a collaborative environment amongst stakeholders with competing requirements. For example, during new product design, fashion buyers, who are primarily responsible for curating designs, choose products with high potential sales and low risk of dead inventory, whereas designers create inherently risky new designs to capture market trends and enhance the brand image of the company. A common explainable forecasting platform for designers and buyers will improve transparency between them and enable buyers and designers to go back and forth with their decisions and design iterations without subjective bias or prejudice. Now we describe our methodology to produce explainable sales forecasts. The forecasting methodology chosen depends on the nature and availability of the data and the target variables chosen, and finally the explainability of the model. The target variables for forecasting models are typically the product performance metrics like sales or sell-through rates. Sales alone do not represent the profits made by a retailer. Sell-through rates are much better indicators because they factor in the amount of inventory received from the supplier. However, predicting the sell-through rates might be tricky because of inventory movements and markdown interventions. Hence, we focus on predicting the first 4-week sell-through rates because our industry partner starts to mark down only after first 4 weeks of introducing new products. The product features are recorded faithfully during the design process, hence their combined effect on sales of individual products can be modeled through regression models. They're also known as design attributes. Apart from product design attributes, there are other factors influencing the sales of products like merchandising factors, which involves markdowns, promotions, visibility, and the date of launch, store locations, weather, holidays, events, market sentiment for similar products, prices of competing products within the store and in the market, and several other macroeconomic factors. In general, any kind of available attributes can be included in the modeling process, and accuracy and explainability of the model depends on the richness of attributes available. For this presentation, we limit ourselves to structured data and exclude the use of any kind of product images. All these attributes, together with the target value of 4-week sell-through rate, can be used to formulate the forecasting problem as a supervised learning problem. We decided to use XGBoost as our machine learning model, primarily because of its scalability, its explainability, its ability to handle missing values, and finally its ability to handle nonlinear relationships. XGBoost derives its explainability from its tree-based nature, and hence we compared XGBoost with other tree-based learners like CatBoost. XGBoost ended up showing better results in terms of accuracy. The predictive model learned can be used to perform post-mortem sales analysis on previous seasons, and it can also be used to perform new product sales forecasting for the upcoming season. This is a valid approach because most new products are characterized by incremental improvements and evolutionary changes in the previous product lines. Hence, features of new products belong to the attribute space of the older products from previous seasons, thus justifying the use of our predictive model for new products. Now we show how we can use the tools of explainability for our predictive models. We can see explainability as answers to these three broad questions, that is, the what, the why, and the what if. So now we'll focus on the what. Under the what category, you can answer questions like, what are the most important attributes affecting sales? What is the effect of patterns on sales? Feature importance plots illustrate the relative contribution of each feature to the model. A higher value of this score when compared to another feature implies that it is more important for the product performance. As one can see from this plot, the 4-week average discount seems to be the most important feature for a predictive model built for the category of T-shirts. To understand the impact of a feature on a corresponding metric, we use partial dependency plots. In this plot, we can see how variations in the 4-week average discount affects the change in 4-week sell-through rate. Under the why category, we can answer questions like, why did this top sell more or less than the average? What are the two top factors responsible for this top selling well? Did this product sell less because of the price or because of the color? While the previous insights were global in nature, that is, they were insights for the sales of the whole category T-shirts, but here we explain the sales for a particular T-shirt. The explanation here shows the factors contributing to push or pull of the predicted metric from its base value to the model output. The base value happens to be the average metric for the whole category. Features pushing the prediction higher are shown in blue, and those pushing the prediction to lower values are shown in red. They are also listed below the plot. In the context of new product forecast, we will be able to explain why this particular product may sell better than the average. As you can see from the plot that this product will have a lower 4-week sell-through rate than average because of the price of 3,000 rupees and the fact that it had a regular cuff. The color saturation and zero discount push this product sell-through rate higher. Under the what if category, we can answer questions like, what if I change the pattern? How much discount should I give this product? What should be the impact of sales if I made the color lighter? What can I change to increase the salability? What if analysis allows us to explain what is the impact of a feature on the target for this particular instance. The plot here shows the impact of changing neckline on the 4-week sell-through rate. This capability is different from the partial dependency plots because here we are focusing on the impact of a feature change on a particular product rather than the entire category. Now we'll talk about sales interventions. What if analysis provided the impact on sales based on the changes of a particular attribute? It can be used by the designer during pre-season design phase to choose the most appropriate attribute to improve sales. It can also be used for merchandising interventions like markdown during in-season scenarios. Now, given a particular product, if we can find the smallest change to its feature value such that its prediction reaches a desired target value, then we have a counterfactual explanation. Counterfactual explanations for black box models have gained popularity over recent years, mainly because they provide a recourse to change the prediction to obtain a more favorable prediction. Now, for example, given this particular product, a counterfactual explanation would suggest the designer to change the neckline from off-shoulder to a crew neck and slightly modify the color as shown in the figure. These minimal changes would improve the first 4-week sell-through rate of this product from 58% to 73%.